Okay, so continuing on with our lecture as part of the pre-lab discussion before we actually begin today's laboratory on measurements, we're going to continue through our note set. We're going to do a few more unit conversion examples, and then finally, once we finish the measurement section of our note set, we'll be able to discuss and begin today's laboratory, which is focused on measurements. So continuing on from lecture, and just to get everyone back in the problem-solving rhythm, I'd like everyone to start working on the following workbook questions. So this is from your provided workbook, and I'd ask you to perform the following conversion. I'd like you to convert 8,911 pounds to milligrams. So let's take about 4 minutes to work through this example, and I have my camera set up, so once we're done with this problem, I'll be able to show you in a calculator how to enter your responses into a calculator. I'll be using the TI-30XA, which is available from most supply stores, and we'll discuss that momentarily. So let's spend about 3 to 4 minutes working on this example, and in order to go from pounds to milligrams, we're going to need some conversions from our table. We're going to need some conversions from our table, which, just as a reminder, is on page 17 of your notes. So does anyone see any conversion factors that relate pounds and grams or milligrams? Does anyone see any conversion factors in our table that relate pounds and grams?
The ounces to grams, or
ounces to grams? Yeah, that's one of them. Are there any other conversions?
Pounds to kg to kilogram to grams.
Yep, we can go from pounds to kilograms, and we also have this pound to gram conversion. Let's use the pound to gram conversion since it's less steps, but any of these conversion factors would work as a bridging conversion factor. So 453.6 grams per pound. Okay, so let me write that down. So we have 453.6 grams is equal to 1 pound. Okay. We also need another equality. 1 milligram is equal to how many grams? 1 milligram is equal to how many grams?
10 to negative 3.
10 to the negative third. Okay. So now that we have our table of conversion factors, I'd like you to take the next few minutes, make a solution map, and complete the unit conversion from pounds to milligrams. And don't be shy to share your responses in the chat or verbally. And we'll spend about another 3 minutes on this example. And if you have your calculator ready, I would get it out to the side because I'll be showing you how to enter values into your calculator in an example such as this. And if there are any questions at all, don't be shy to ask them verbally or in the chat. The reason why we're covering and we're continuing to go through the note sets is it really sets us up nicely for the laboratory today. And if you're stuck, you can also message in the chat your proposed solution map, and I'd be happy to provide feedback. And we'll discuss in another 2 to 3 minutes.
I guess I'm confused on how to set it up and what to put what on top and what to put what on bottom.
Okay, let's work through this example together and let's talk about each of these aspects. So first, let's make a solution map. So what are our starting units? So we're talking about pounds and milligrams. What are our starting units?
Pounds?
Yes, exactly right. So we have 8,911 pounds. And what's our end goal? What final units do we want to reach?
Milligrams?
Yep, exactly right. So looking at our table of English to metric conversion factors, what is our bridge between the English and metric system? What relationship can we use that gets us from the English system of pounds to the metric system of grams or milligrams? Is there a conversion factor, or is there an equality that we have that relates pounds and milligrams or grams?
Is it the 453.6 grams?
Exactly right. So this is what I like to call our bridging equality. It relates pounds to grams. So we can go from pounds to grams. And now that we're in the metric system, we have free rein to go to another prefix unit. Can we go from grams to milligrams pretty easily? Do we know how to do that? Or can we go from a base unit to a prefix unit relatively easily?
Yeah, right. We can just convert it to grams.
Mm-hmm. Yep, we've done this kind of conversion before. So now that we're in the metric system, we can very easily go to our prefix unit. So now we have our complete solution map. So now what we're going to do is we're going to execute on the solution map. So we have 8,911 pounds. Okay. And now what we're going to do is, if we're going from pounds to grams, so drawing our arrow, grams is, if we're going 2 grams, what units will go on top? If we're going 2 grams, what units will go on top?
Grams?
Exactly right, exactly right. So that in turn gives us 453.6 grams per every 1 pound. Perfect. Now for the next step. So we've set up our first unit conversion. Now for the next step, I'm just finding the right pen to show the second step. For the next step, we're going from grams to milligrams. And since we're going 2 milligrams, what units go on top?
Milligrams.
Yep, exactly right. So we have 1 milligram, and then on the bottom, we have how many grams?
10 to the negative 3.
Exactly right. And now what I'm going to do is I'm going to turn on my camera, which is facing the back of my tablet, and I'm going to show you on the TI-30XA. So here's our TI-30XA calculator. Let me zoom out a little bit. Okay, and now what we're going to do is I'm going to show you the exact order of buttons that you need to push in order to compute powers of 10. Okay, so first and foremost, the on button will set things to 0. Let me just make one quick edit to my video settings because it loves to mirror my video. Okay, there we go. Now it's no longer mirrored, so it should be a little less confusing now. Okay, so to compute powers of 10, you're gonna hit the EE button. So to compute powers of 10, you hit the 1 button. So we see a 1, then you hit the EE button, and you'll see these numbers pop up in the upper right-hand corner. Now we can enter our power of 10. For example, if I push 9, this is equivalent to 1 times 10 to the 9th. So if I hit equals, lo and behold, I get a really large number. That's 1 times 10 to the 9th. Let's clear it, and let me show you how to do negative powers of 10. So we hit 1, so we see 1. And now what we're going to do is we're going to hit EE. Okay, and to do negative powers of 10, you'll see this little sign change symbol, plus minus. You're going to push that button, and as you see, there's a negative sign. Does everyone see that negative sign? So if we want to do negative third, we hit a 3. And just to check your work, we see 1 times 10 to the negative third. If we wanted to compute that out, we hit the equal sign, and lo and behold, it will give us the long form value of 1 times 10 to the negative third. Now, there's a really cool button in your calculator. If you hit the second key, the green button, this turns on secondary functions. Now, if we notice, does everyone see these little green letters? There's some green letters above each of your numbers. Now, above the number 5 is a button called scientific, SCI. So if we hit second and 5, it will convert your number into scientific notation. Likewise, if you hit the second button and the 4 key, which is known as the flow key, it will convert any number in scientific notation to a decimal. Does this make sense to everyone so far? Is everyone comfortable with this idea so far?
I don't have my calculator yet.
It's okay. That's part of why I'm recording this as well.
Okay, awesome. Thank you.
So let's show how we'd enter this in our calculator. So I'm going to enter 8,911. So I see 8,911 pop up times and then 453.6. So I hit the times symbol and then 453.6. And now I hit the equal sign. So I end up with a large number. Now, if I'm dividing, I'm going to hit the division symbol. And then I'm going to enter 1 EE. And now for a negative power of 10, I hit the sign change symbol. We see that negative sign pop up, and then I hit 3. So this is 1 times 10 to the negative third. Now I'm going to hit the equal sign, and I should get out the following really long number. Now, we have a trick. If I want to view this number in scientific notation, all I have to do is hit the second button, and then the flow, and then the scientific key, which is above 5. So second, psi, and now I have my number written out in scientific notation. So this is 4.04, and it's positive 9. So 4.04 times 10 to the positive 9. So just to show that process one more time. So I enter 8,911 times 453.6. So that gives me a large number. Let me set it to flow. So here's the long form number that you'd see. Then you hit the division symbol, and then we enter 1 EE. You hit the negative sign button. So does everyone see that negative sign? And then we hit 3. So we have 1 times 10 to the negative third. Now we hit equals to finish our division operation, and we end up with the following long form number. Now what we're going to do is we're going to hit second and then the science key. And now we've converted our number into scientific notation. So let's write that down. So that gives us 4.046 times 10 to the 9th milligrams. So our answer most closely matches response B. Does that make sense to everyone? Is everyone feeling a little more comfortable taking measurements with their calculator?
Professor, I have a question about the step you're dividing it to the 10 to the power of -3.
Yes.
So instead of doing that, can we just multiply it by 1,000? So bring the
Yes,
10
you're more than welcome to do that as well.
to that. Okay.
That would work equally well. I was just showing everyone how to handle entering powers of 10 and dividing by powers of 10 in the calculator, and that's part of why I chose this example.
Okay, got it. Thank you.
How do you remove powers of 10? You'd have to clear and restart entering from scratch. Once you hit the EE button, it's sort of set. Oh, by remove powers, you mean get rid of scientific notation? Good point.
Because when I put it on, like the powers are just like stuck on there and I don't know how to remove it.
So I have it set in scientific notation right now. So you hit the second button and then the 4 key, which is known as flow.
Oh, okay, thank you.
And now the number is in long form.
Okay.
Does that make sense?
Yeah, that's better.
Perfect, perfect. So if there are any questions you'd like me to show you how to enter into the calculator, don't be shy to ask. I'm gonna switch to tablet mode as we continue on with these next few examples, so I can use some of the additional tablet features when I'm presenting my lecture. Okay, so everyone did a great job on this example. Let's keep going now and let's talk about another concept, another type of unit conversion. And this is related to temperature. So, first and foremost, temperature is a measure of the amount of molecular motion in a sample. So at 0 degrees Celsius, we have a relatively small amount of molecular motion. Well, suppose we're at 100 degrees Celsius, we have a large amount of molecular motion. So temperature serves as a proxy for the amount of molecular motion in our sample. Now, the metric system utilizes units of Celsius and Kelvin. Unfortunately, in the English system, we use units of Fahrenheit. Thankfully, there is a defined conversion factor to convert between Fahrenheit and Celsius. So the main formula that we're going to use to convert between Fahrenheit and Celsius is that the degrees Fahrenheit is equal to 1.8 times 1.8 times the degrees Celsius plus 32. No parentheses there. So if we wanted to go from Celsius to Fahrenheit, you'd plug in the temperature in Celsius here and then add 32. The other form of this equation that you most commonly see is that degrees Celsius is equal to degrees Fahrenheit minus 32 times 5/9. In other words, dividing by 1.8. So these two equations represent the two pillars of Fahrenheit to Celsius conversions. Now, the most common temperature unit in chemistry are Kelvin. Now, kelvins are really useful because they're an absolute scale, so there are no negative values. This is really important because many equations in chemistry require you to enter the temperature in Kelvin because entering a negative temperature value would result in an output that doesn't make physical sense. So Kelvin is an absolute scale. It goes from 0 to very large numbers. Absolute scale, no negative numbers. When you're performing a calculation in chemistry, kelvins should overwhelmingly be used for your temperature measurements. So kelvins are equal to degrees Celsius plus 273.15. So it's a nice, simple conversion. To help everyone visualize the relationship between Kelvin, degrees Celsius, and Fahrenheit, the boiling point of water is 212 degrees Fahrenheit, 100 degrees Celsius, and 373 Kelvin. Body temperature of 98.6 is 37 degrees Celsius and 310 Kelvin. Freezing point of water is 0 degrees Celsius, 32 Fahrenheit, and 273 Kelvin. And room temperature is around 77 degrees Fahrenheit, 25 degrees Celsius, and 298 Kelvin. So as you see, Fahrenheit, Celsius, and Kelvin are quite different, even though they're describing the same temperature. Let's practice doing some conversions. So I'm given the following two equations. Let's first convert 68 degrees Fahrenheit to Celsius. In this case, we're going to use our other conversion factor where degrees Celsius is equal to degrees Fahrenheit minus 32 divided by 1.8, which could be also written as degrees Fahrenheit minus 32 times 5/9. So If we're converting 68 degrees Fahrenheit to Celsius, we're solving for Celsius. So we plug in 68 minus 32 over 1.8. And if we punch that into our calculator, that in turn gives us 20 degrees Celsius. Let's do a Kelvin conversion now. We're asked to convert 37 degrees Celsius to Kelvin. We know that Kelvin is equal to degrees Celsius, which is 37.0 degrees Celsius plus 273.15. 37 plus 273.15 gives us 310.15 Kelvin. Not degree Kelvin, just Kelvin. Does this make sense to everyone? Any questions? Yes.
Professor, the book said that it's class 27.3.
Yes, the 273.15 is more accurate, but if you just do plus 273, that's more than okay. It's the same conversion factor. The book just removed the last 2 decimal places.
Can you show me how you got 20 Celsius? For some reason, I wasn't getting that answer.
Okay. So if we, so just to break this down, 68 minus 32 gives us 36, and then 36 divided by 1.8 gives us 20. Does that make sense when you enter that step by step in your calculator?
Yeah, I think I wasn't equaling out first before I divided it.
Yes. In that case, the way your calculator will view it is it'll take 68 minus 32 divided by 1.8. So it doesn't split it up into orders of operations. If you enter this term in parentheses, exactly as I wrote it out, then your calculator will recognize to subtract first and then divide. Does that make sense?
Yes, thank you.
Perfect, perfect. So now that we've done a few examples, let's do one more where we have to go from Fahrenheit to Kelvin. Okay, so we're starting off with Fahrenheit and we're trying to go to Kelvin. And just like before, what is our stepping stone? What is our intermediate unit? What unit are we going to go through? Celsius, exactly right. So we're going to go from Fahrenheit to Celsius to Kelvin. Perfect. So let's do the first step. So Celsius is equal to degrees Fahrenheit minus 32 over 1.8. Okay, so plugging in, we have 72 degrees Fahrenheit minus 32 over 1.8. And that in turn gives us, so we have 72 minus 32 over 1.8. And that gives us 22.22 degrees Celsius. We're carrying excess digits just so that way we don't end up with rounding errors. And for Kelvin, it's equal to degrees Celsius plus 273.15. So we have 22.22 plus 273.15. And that in turn gives us 295.37, which we'd in turn round to 295. But both of these answers will be accepted as of right now, but we'll learn later on in the class significant figure rules, and that'll explain why I rounded this number to 295. Does this set of conversions make sense to everyone? Is everyone comfortable with these unit conversions? Allow me a moment to just mute someone really quickly. And oh, sorry, you're more than welcome to unmute and ask a question. I just noticed some background noise. Sorry about that. Now that I cleared the background noise, you're welcome to unmute and ask your question. Did you have a question? I noticed someone was starting to talk.
Yes, that was me. Sorry.
Oh, no, no problem at all.
How did you get the 22.22 Celsius?
So if we take step 72 minus 32, we end up with 40. And then if we divide by 1.8, remember to enter your operations step by step into your calculator.
Okay.
Are you getting the same result as me?
Okay. Yes. Now I just missed that step there.
Otherwise, what you can do is you can enter a parentheses in before you complete your subtraction operation, and your calculator will do the subtraction operation first. Either method is acceptable.
Thank you.
Okay. Any other questions on these examples that I can address?
I have a question.
Yes, please go ahead.
Where'd you get the 32?
That's part of our conversion factor. So if we look at our equation for converting between Celsius and Fahrenheit, we see that Celsius is the degrees Fahrenheit minus 32 over 1.8. And this is the equation to convert between Celsius and Fahrenheit.
Oh, okay. Thank you.
Perfect.
And then I had another question.
Yes.
Where did you get the 273.15?
That's our conversion from Kelvin to Celsius. It's okay. No problem at all. That's part of why I provided these conversions at the top. And these are conversions that you should be familiar with for the exams and homework.
So we're always going to use those numbers, 32 and 273.15?
This is a fixed conversion factor, just like the conversion factors that we've learned to go from prefix to base units. They're fixed numbers that'll always be the same when you're converting between Celsius and Fahrenheit and Celsius and Kelvin.
Oh, okay. Thank you.
Perfect. Any other questions that I can address? If not, let's apply what we've learned, and I'll provide you the Celsius conversion. So the degrees Celsius is equal to the degrees Fahrenheit minus 32 over 1.8. And I'd like you to now work on the following two examples. I'd like you to convert 32 degrees Fahrenheit to Celsius and 25 degrees Celsius to Kelvin. We'll spend about 2 to 3 minutes on this example, and then we'll discuss momentarily. And I'm already seeing some reasonable responses in the chat, and we'll discuss this example in about another 2 to 3 minutes. And the responses I see in the chat look great so far. Spend about another 1.5 to 2 minutes, and then we'll discuss. Let's try to get a few more responses in the chat, or if you have a question, don't be shy to ask your question in the chat or verbally. Let's try to get a few more responses in the chat before we discuss. And the responses I see in the chat look reasonable. So let's now discuss these examples. So first, if we're converting 32 degrees Fahrenheit to Celsius, the degrees Celsius are equal to the degrees Fahrenheit minus 32 over 1.8. So we take 32 minus 32 over 1.8, and that gives us a degrees Celsius of 0 degrees Celsius. Let's look at this next example. We're asked to convert 25 degrees Celsius to Kelvin. We know that kelvins are equal to the degrees Celsius plus 273.15. So that gives us 25 degrees Celsius plus 273.15. So our temperature in Kelvin is equal to 298.15 Kelvin.
Professor, for the 30, the one above it, what did we do with the 1.8? Does that not matter anymore?
You still divide by 1.8, but 0 divided by 1.8 is still going to be 0. Does that make sense?
Thank you.
Perfect. So now let's put together these two unit conversions and let's do a multi-step conversion. So this time I'm asking you to convert 100 degrees Fahrenheit to Kelvin. So let's spend about 2 to 3 minutes on this example and then we'll discuss together. The recordings will all be posted on Canvas. For waitlisted students, if you're added to the class, you'll have access to all of the lecture recordings as well as the lab recording. And they're also on the course YouTube channel as well. And the responses I'm seeing in the chat look reasonable so far. Let's try to get a few more responses and then we'll discuss. We'll spend about another 30 seconds to a minute before we discuss. Okay, so first and foremost, we're trying to go from Fahrenheit to Kelvin. So we're going through our intermediate unit of degrees Celsius. So we know that degrees Celsius are equal to Fahrenheit minus 32 over 1.8. So that in turn gives us 100 degrees Fahrenheit minus 32 over 1.8. That in turn gives us 37.78 degrees Celsius. We know that Kelvin are equal to degrees Celsius plus 273.15. That gives us 37.78 plus 273.15. And that in turn gives us 310.93 Kelvin, which would in turn be rounded to, following the sig fig rules, to 311 Kelvin. Does this make sense to everyone so far?
So Professor, we never leave a decimal point for temperature. That's what I understand, right?
So not necessarily. In this case, we round to get rid of the decimal places because I'm following some sig fig rules that we are going to discuss later on in the note set.
Okay,
Does that make sense?
it does. Thank you.
Perfect. Okay, so we're very comfortable with unit conversions. So another type of unit conversion, another type of unit that we commonly encounter in chemistry are what are known as composite units. So composite units are a unit of measurement that contains two or more base units. So for example, density, which is a common physical property that's measured for different substances, is expressed in grams per milliliter. Volume is expressed as centimeters cubed. Velocity or speed is commonly represented in meters per second. Now, you can think of composite unit conversions as two discrete unit conversions lumped together. So for composite unit conversions, let's look at an example and let's show the problem-solving process to convert between composite units. So first and foremost, you handle each unit in the composite unit individually. You identify your starting and ending units, and you go through the base unit. So in this case, we're starting off with 430 micrograms per milliliter, and we're asked to convert to milligrams per microliter. Okay, so let's treat this composite unit as two separate unit conversions. So first things first. We're going from micrograms to milligrams. So what is our stepping stone? What is our stepping stone on top? What is our intermediate unit on top? To go from micrograms to milligrams. Grams. Yep, so we're going to go to grams per mil and then to milligrams per mil. Okay, so we've completed the first top half of our unit conversion. We still have the bottom half to deal with. So in the bottom half, we're trying to go from milliliter to microliter. So what is our intermediate stepping stone to go from 1 over milliliter to 1 over microliter? What's our stepping stone? Liters. So we're going to go to milligram per liter. So notice how, in effect, we have two unit conversions lumped together. Does everyone see that? On the top, first, we're going from micrograms to milligrams, and on the bottom, we're going from 1 over milliliter to 1 over microliter. Okay, so step by step, we're going to start with one of our prefix units. So we're going to deal with the top part first. So we're going from micrograms to grams to milligrams, okay? So if we have 430 microgram per mil, and our goal is to end up at milligrams per mil, we're going to need to set up some unit conversions. So first, let's go to the prefix unit, from the prefix unit to the base unit. So if we're trying to go from micrograms to grams, just to start us off nice and slow, we know that 1 microgram is equal to how many grams? What does the micro prefix correspond to? 10 to the negative 6, exactly right. Okay, perfect. So to go from micrograms per mil to gram per milliliter, we need to multiply by our conversion factor. Since we're going from micrograms to grams, we're gonna want what unit on top? If we're going from micrograms to grams, what unit goes on top? Grams, exactly. So we know we have 10 to the negative 6 gram per microgram, and that in turn gives us 430 times 10 to the negative 4th gram per mil. Notice how the milliliter units don't disappear. Oops, sorry, this shouldn't be 430, it's 4.30 times 10 to the negative 4th. And you get this when you punch these two numbers together into your calculator. Any questions on this first step? So this is something that we've likely seen before in our prefix to base unit conversions. Let's continue on now. And considering that we now have 4.30 times 10 to the negative 4th gram per mil, and our goal is to go from grams, looking at our solution map, our goal is to go from grams to milligrams. So we know 1 milligram is equal to how many grams? 1 milligram, what does the milli prefix correspond to? 10 to the negative 3rd gram. Perfect. So then, if we want to go from grams to milligrams, what units do we put on top? What units do we put on top? Milligrams, exactly. And we know 1 milligram is 10 to the negative 3rd gram. The grams cancel, and we're left with 4.30 times 10 to the negative 1st milligram per milliliter. Notice the milliliters still haven't been addressed. Does this first step make sense? This first step we've done actually a few times today and in this past lecture. Does this make sense so far? Perfect. Okay, so we've converted our first prefix unit. So now that we're left with 4.30 times 10 to the negative 1st milligrams per milliliter, if our end goal is milligrams, let's look all the way at the start of our problem. Our end goal is milligrams per microliter. So then we need to go from 1 over milliliter to 1 over microliter, and we identified our intermediate unit as 1 over liter. Now, the one thing that I'd like you all to keep in mind, because this unit of milliliters is in the denominator, we're converting, instead of milliliters, we're converting 1 over milliliters into 1 over microliters. So we have to be really careful with how we set up our unit conversion factors. So now that we have our solution map, let's write out an equality. We know 1 milliliter is 10 to the negative third liter, and we know 1 microliter is equal to 10 to the negative sixth liters. Okay, so if we're starting off with 4.30 times 10 to the negative first milligram per milliliter, if we want to cancel our milliliters and we want to go from 1 over milliliter to 1 over liter, where does our unit of liters need to be? On the top or the bottom? And really just look at our solution map and tell me, where does our unit of liters need to be? On the top or on the bottom? So our unit of liters in our solution map needs to be on the bottom. So we put our unit of liters on the bottom. And then if we want to cancel our unit of milliliters, what needs to go on the top? Milliliters, yep. So in 1 milliliter, we have 10 to the negative third liter. Notice how in this setup, the milliliters are on opposite sides of our dividing line and they cancel. And we're left with liters on the bottom. Does that make sense to everyone? You place your units in the solution map in the exact same spot in your conversion factor. Liters on the bottom, liters on the bottom. Let's do another example. If we're going from 1 over liter to 1 over microliter, where do microliters need to go? On the top or the bottom? Bottom, yep. So we know in 1 microliter, we have 10 to the negative 6 liters, and that allows our liters to cancel. So if we multiply by our conversion factors, so just rewriting our solution once again, we have 4.30 times 10 to the negative first milligrams per milliliter. We know in 1 milliliter, there are 10 to the negative third liter. And we know that we have 10 to the negative sixth liter per 1 microliter. Milliliters cancel, liters cancel, and we're in turn left with 4.30 times 10 to the negative fourth milligrams per microliter. And this is after you enter each of these numbers into your calculator. Does that make sense to everyone so far? Okay, so let's keep going now and let's talk about just a general rule of thumb. You want to choose a conversion factor that contains your desired unit in the same location as the units in your final answer. Additionally, you want to choose a conversion factor containing your starting units on the opposite side of the dividing line. So let's look at an example. We're asked to convert 350 kilograms per milliliter into micrograms per kiloliter. So I'm going to treat these unit conversions piecewise. So first things first, looking on the top, I have kilograms. I want to get to micrograms. What is my stepping stone? What intermediate unit gets me from kilograms to micrograms? Grams. So I'm going to go to units of gram per mil. Wonderful. And now for my second And then once I'm at gram per mil, I'm going to go to microgram per mil. Okay. Now for the next conversion, the next prefix unit, I'm starting with units of milliliter. I want to get to units of kiloliter. So what stepping stone do I need to go through? Liter. So I have 1 microgram per liter. Oh, let me just say units of microgram per liter. We'll fill in the exact numbers momentarily. Okay, so now that I have my solution map set up, I'm going to write some equalities. I know 1 kilogram corresponds to 10 to the 3rd gram. 1 microgram corresponds to 10 to the negative 6th gram. 1 milliliter corresponds to 10 to the negative 3rd liter. And 1 kiloliter corresponds to 10 to the positive 3rd liter. Okay, so now that I have my tools that I'm going to use for this conversion, I'm going to write my starting number, 350 kilograms per mil. Now, following my solution map, if I'm going from kilograms to grams, in my conversion factor, what units do I need to have on top? What units do I need to have on top? Grams. So I know that I have 10 to the 3rd grams, and what units do I need to have on the bottom? Kilograms. Okay, kilograms cancel. We're good to go. Okay, let's do our next step. We're going from grams to micrograms. So then, what units need to be on top? Micrograms, exactly right. And we know in 1 microgram, we have 10 to the negative 6 grams. So grams cancel. We're on the right track. Now let's deal with milliliters. We're going from 1 over milliliters to 1 over liters. So looking at our solution map, where do we need to place our units of liters? On the top or on the bottom? On the bottom, right? So we have units of liter on the bottom and units of milliliter on the top. And we know in 1 milliliter, we have 10 to the negative 3rd liter. Finally, we're going from 1 over liter to 1 over kiloliter. So where do we place our units of kiloliter? On the top or on the bottom? Where do we place our units of kiloliter? On the top or on the bottom? On the bottom. So we know in 1 kiloliter, we have 10 to the 3rd liter. Units of liters cancel, units of milliliters cancel. And now all we have to do is punch this into our calculator. So this in turn gives us 350 times 10 to the 3rd times 10 to the 6th times 10 to the 3rd times 10 to the 3rd, and this is micrograms per kiloliter. That in turn, after punching it into our calculator, gives us 3.50 times 10 to the 6, 12, 15, 17. 3.50 times 10 to the 17th microgram per kiloliter. Does this make sense to everyone so far? Okay, so let's try to apply what we've learned to the following example.
Right to exit 10.
Sorry, what was that? Sorry, did you have a question? Is there a question I can address? If not, let's try to work on the following example. So let's try to perform the following unit conversion. We're going from nanograms to microliter to milligrams per deciliter. So I'll give everyone about 4 to 5 minutes to work on this conversion, and then we'll discuss momentarily. And don't be shy to ask any questions you have in the chat or submit your proposed solution in the chat. And we'll discuss this example in about 4 minutes. And let's try to get a few responses in the chat. In worst case, you can type your proposed solution map in the chat so I can provide feedback. And let's try to get a few more responses in the chat, and then we'll discuss in about another 3 minutes. And let's try to get a few more responses in the chat before we discuss in about 2 minutes. Okay, so let's take a look at this example. So first we're going to write out our solution map. So we're starting off with 0.154 nanograms per microliter. Okay? So our end goal at the end of all of this unit conversion process would be units of milligram per deciliter. Okay, so let's treat these unit conversions as two separate cases. So let's start on the top. We're trying to go from nanograms to milligrams. So what are our intermediate units? What units are we going to go through? From nanograms to milligrams, we're going to go through units of grams. So we end up with grams per microliter, followed by milligrams per microliter. That's our first step. And now for our second step, as many of your classmates have noted, if we want to go from microliter to deciliter, what intermediate units will we go through? What intermediate units? We'll be going through liters. So we'll be going from milligrams to microliter to milligram to liter to milligram per deciliter. Perfect. Now that we have our solution map, let's write out some equivalencies. So 1 nanogram is equal to 10 to the negative 9th gram. 1 milligram is equal to 10 to the negative 3rd gram. 1 microliter is equal to 10 to the negative 6th liter. And what does a deciliter equal? What does a deciliter equal? 10 to the negative 1st. Wonderful. Now that we have this solution map and our set of equalities, what we're now going to do is we're going to begin our unit conversion. So we have 0.154 nanogram per microliter. Okay, for our first step, we are going from nanograms to grams. So we're going to have units of grams on top. So we have 10 to the negative 9th grams per 1 nanogram. Nanograms cancel. For our second step, we're going to go from grams to milligrams. So in this case, we know in 1 milligram, we need milligrams on top because that's what we're going to. We have 10 to the negative 3rd gram. Okay. Continuing on, if we're going from 1 over microliter to 1 over liter, where do our units of liters go? On the top or the bottom? On the bottom, exactly right. So we know 1 microliter corresponds to 10 to the negative 6th liter. Continuing on, going from liter to deciliter, or 1 over liter to 1 over deciliter, we're going to have units of deciliter on the bottom, and that corresponds to 10 to the negative 1st liter. So microliters cancel, liters cancel. And so entering this into the calculator, we have 0.154 times 10 to the negative 9th times 10 to the 3rd times 10 to the 6th times 10 to the negative 1st milligrams per deciliter. So that in turn gives us 1.54 times 10 to the negative 2nd milligrams per deciliter. There we go. Any questions on these examples?
Yeah, so the first in the beginning where we go from nanograms to micrograms, and then it converts to grams to nanograms. How do we get to the mg over the micro?
So first and foremost, so when you go from nanograms, we're going from nanograms to grams to milligrams. The microliters just stay the same in this first step of unit conversions because we aren't actually dealing with the microliter units just yet. So we're going from nanograms to grams using the following conversion factor, and then we're going from grams to milligrams using our second conversion factor in blue. That gives us units of milligrams per microliter. Then we convert our units of microliter to liter and deciliter in our second set of unit conversion factors.
Oh, I see.
Does that answer your question?
Yeah, okay, got it.
Unit conversions for on top don't affect the units on the bottom just yet. Unless we're explicitly trying to cancel out microliters, that unit will just stick around and be carried through our conversion. Does that make sense?
Yes.
Perfect. Any other questions I can address? Okay, so let's look at another type of composite unit, and these composite units are known as cubic and square units. Now, the only thing you need to be careful of with cubic and square units is that you need to make sure you convert each component of a cubic or square unit. So in this case, we're asked how many centimeter cubed are in 150 millimeter cubed. So our starting unit is 150 millimeters cubed. Now, if our end goal is centimeter cubed, what should our stepping stone be to go from millimeters to centimeters? What's our intermediate unit? What's our base unit? Meters, exactly right. But instead of just normal meters, since we're dealing with cubic units, it will be meters cubed. Now, there are two methods of dealing with this. First, you can start by writing out your equalities. We know 1 millimeter is equal to 10 to the negative third meter, and 1 centimeter is equal to 10 to the negative second meter. Wonderful. Okay, we have our conversion factors established. We have our equalities established. Now we're going to start to try to convert. And I'm going to write this millimeters cubed in its expanded form, which is 150 millimeters times millimeters times millimeters. Okay? And now, if I wanted to go from millimeters to meters, what units do I need to have on top? What units do I need to have on top? Meters. So I know I have 10 to the negative third meter per 1 millimeter. And I've canceled one of my millimeter units, but am I done? Is this a complete conversion? Have I converted all of my millimeters into meters? No. And that's why I really like everyone to write out their units. So we have 10 to the negative third meter per 1 millimeter. So we'll cancel our second millimeter, and then we'll finish by multiplying one more time by 10 to the negative third meter per millimeter, which cancels our last millimeter unit. Another way of thinking about this is we can have 150 millimeters cubed, and then we're multiplying by our conversion factor of 10 to the negative third meter per millimeter, except we're cubing our conversion factor. In both cases, we get the final answer after our first step of 150 times 10 to the negative 9th meter cubed, which is equivalent to 1.50 times 10 to the negative 7th meter cubed. We're not quite done here, so now we have to go from meter to meter cubed to centimeter cubed. So we have 1.50 times 10 to the negative second meter cubed. And my question to all of you is, what unit do we need to have on top? What unit do we need to have on top? And I'm going to write this as meter times meter times meter, just so that way no one forgets to convert every single one of these units. We want centimeters on top, exactly right. And we know 1 centimeter corresponds to 10 to the negative second meter. We've canceled one of our meters. Are we done? Have we converted everything successfully? No, obviously not, right? We still have two more meters floating around. So we have 1 centimeter over 10 to the negative second meter. So we canceled our second meters, and then 1 centimeter over 10 to the negative second meter. We've canceled our third meters, and that in turn gives us 1.50 times 10 to the negative 7th meter cubed times 1 over 10 to the negative second times 1 centimeter over 10 to the negative second meter cubed. And if we punch out either of these expressions in our calculator, we get 1.50 times 10 to the negative first meter cubed. Oops, not meter cubed. Meters canceled. Centimeters cubed. There we go. Perfect. So the only thing that's tricky about cubic units is you need to convert every single one of our units. Ah, yeah. So 150, so this 150 is equivalent to 1.50 times 10 to the second. And 2 minus 9 gives us negative 7. You would also get this result if you punch this directly into your calculator. Does that address your question? Perfect. Any other questions I can address? Okay, so now that you've seen some examples, let's try to apply what we've learned. So I'd like you to tackle the following 2 conversions. We'll spend about 5 to 6 minutes on these 2 examples, and I'd like you to submit your responses in the chat, or you can unmute and propose your responses verbally. We'll discuss these examples in about 5 to 6 minutes, and if you have any questions, don't be shy to ask them in the chat or verbally. And don't be shy to submit your responses in the chat or any questions that you have in the chat. let's try to get a few more responses in the chat and we'll discuss in about another 4 to 5 minutes. Let's try to get a few more responses in the chat and then we'll discuss in about another 3 to 4 minutes. And if you have any questions at all or would like to submit your proposed solution map, don't be shy to message that in the chat or unmute and write out your solution map verbally. And if you have any questions, don't be shy to ask them in the chat. I'd be more than happy to help answer any questions that you have. And we'll discuss in about another 2 to 3 minutes. Okay, so let's look at this first example. So in this first example, we're asked to calculate how many micrometers cubed are in 4.5 times 10 to the first decimeter cubed. Just for reference, this recording should be posted by tomorrow afternoon at the latest. So first things first, let's write out our starting units. We have 4.5 times 10 to the first decimeter cubed. And our end goal is micrometers cubed. Okay, so what intermediate unit can we go through? What is the base unit associated with decimeter cubed and micrometer cubed? Meters, yep, but instead of just normal meters, it would be meters cubed. Okay, now continuing on, we know that 1 decimeter corresponds to 10 to the negative first meter, and we know 1 micrometer corresponds to 10 to the negative sixth meter. Okay, so starting off with 4.50 times 10 to the first decimeter cubed, we know that if we're going from decimeter to meter, we need what units on top? We need what units on top? Meter, yep. So we have 10 to the negative first meter per decimeter. Now, since we have decimeter cubed, we need to multiply by our conversion factor 3 times. Okay, now if we're going from meter cubed to micrometer cubed, what units need to be on top? What units need to be on top? We're going from meter to micrometer cubed. We need micrometer on top. So in 1 micrometer, we have 10 to the negative 6 meter. So we've canceled one of our meters, but are we done? Are we done? Have we canceled everything? No. So we need to continue. We know 1 micrometer corresponds to 10 to the negative 6 meter, and 1 micrometer, let me write that a little more clearly, corresponds to 10 to the negative 6 meter. So if we punch that into our calculator, we have 4.50 times 10 to the first times 10 to the negative third times 10 to the 18th micrometer cubed. That gives us 4.50 times 10 to the 16th micrometer cubed. Does this make sense to everyone so far? If you punch this string into the calculator exactly as written, you will get this same result. Does someone have a question I can address?
So the 6 times 3, that's what equals the 18, the 10 to the 18?
Yep, because we have 3 10 to the negative 6 on the bottom, so we move them to the top. Yep, that's exactly right. Any other questions I can address on this example? Is everyone comfortable with these cubic unit conversion examples?
I think I need a little more practice, and then maybe.
Okay. Yep, definitely. We'll do another example here. This time we're combining a composite unit and a cubic unit conversion. So remember, treat composite units as 2 different unit conversions and process them step by step. So I'll give everyone about 4 to 5 minutes on this example, and then we'll discuss. And don't be shy to message me with any questions you have or your proposed solution map. I find the act of practicing and working through a problem can in turn help reveal any questions that you have and can help you develop a lot of the skills necessary to work through these problems in the future. And don't be shy to message your proposed solutions in the chat. My office hours are noted in the syllabus, and I have office hours Monday, Tuesday, and Thursday. And I can give you the times at the end of this laboratory session. And don't worry, this problem in particular is about as difficult as it's going to get for unit conversions. But I wanted to have everyone opportunity to attempt this example, and then we'll go over the solution. So as to provide everyone a little bit of guidance and to help everyone sort of zero in on the solution. So let's first make a solution map. When in doubt, go back to the basics that we've learned at the start of this section. So we have units of kilogram per kilometer cubed, and we're trying to go to our final units of microgram per centimeter cubed. Let's deal with our top units first. So we're trying to go from kilograms to micrograms. So what is our intermediate unit? What is our intermediate unit? Grams, yep. So we're going to grams per kilometer cubed, and then finally to micrograms. Whoops, one moment. And then to microgram per kilometer cubed. Allow me 1 second. Sorry, sometimes OneNote is mildly laggy. Give me 1 second just to allow OneNote to catch up to what I'm writing. Okay, so we have 1 microgram per kilometer cubed. Now for our next step, we're trying to go from kilometer cubed to centimeter cubed. So what is our intermediate unit going to be? If we want to go from kilometer cubed to centimeter cubed, we go through units of meter cubed. Okay, now let's write some equalities. We know 1 kilogram is 10 to the 3rd gram. We know 1 microgram is 10 to the negative 6th gram. We know 1 kilometer is 10 to the 3rd meter, and 1 centimeter is 10 to the negative 2nd meter. These are all from the table of unit conversions that I provided you. Okay. Continuing on now, let's handle our first unit conversion. So we have 1.6 times 10 to the 15th kilogram per kilometer cubed. Just like before, we're going from kilogram to gram. So how many grams are in a kilogram? How many grams are in a kilogram?
10 to the 3rd.
Yep, exactly right. Okay, continuing on, we're going from gram to microgram. So what units need to be on top?
Microgram?
Yep, exactly. So in 1 microgram, we have 10 to the negative 6th grams. Okay, perfect. Now, continuing on from there, we're going from kilometer cubed to meter cubed. Okay, so then what units do I need to have on the bottom? Meters or kilometers? What units do I need to have on the bottom? Meters, yep, exactly right. And I need kilometers on top. So we have 1 kilometer for every 10 to the 3rd meter. Now, since it's a cubic unit, we're going to need to write out our conversion factor a total of 3 times to cancel each of our kilometer units. Okay. Now for the final part of our conversion, we're going to need to go from meter cubed to centimeter cubed. So then we're going to put centimeter on bottom. So we know we have 10 to the negative 2nd meter per centimeter. Now, one other way, instead of writing out your unit conversion factor 3 times, is to instead cube your conversion factor. So let's unpack this a little bit. So when we cube our conversion factor, this is equivalent to saying we have 10 to the negative second times 10 to the negative second times 10 to the negative second meter cubed per centimeter cubed. So we're essentially, cubing the unit conversion factor is essentially the same as multiplying it by itself 3 times. What do you mean by the cube only applies to the kilometer? There are 3 kilometer units in kilometers cubed, and we have to convert each of them individually, just like we convert each of our meter units individually using this cubic conversion factor.
When I was trying it, I was cubing the grams as well. Like I was going to cube steps, but it's only applying to like the denominator basically.
Yeah, exactly. Okay, perfect. Okay, so if we punch this entire string into our calculator, that gives us 1.6 times 10 to the 15th times 10 to the 3rd times 10 to the 6th times 10 to the negative 9th times 10 to the negative 6th. And this has units of micrograms per centimeter cubed. And if we write this out, that gives us 1.6 times 10 to the, this here gives us 24 minus 15 times 10 to the 9th micrograms per centimeter cubed. There we go. Does this make sense to everyone? Does this make a little bit more sense now? We're combining the two concepts, composite units and cubic units, together. And this is about as difficult as the questions are going to get for unit conversions.
Professor, I have a question.
Yes.
So at the very bottom, it says 10 to the 15th, 10 to the 3rd, and then 10 to the 6th. Wouldn't that be 10 to the negative 6? Or maybe I'm...
Oh, it's because when you move a unit on the, when you move the power of 10 on the bottom to the top, the sign changes.
Oh, we moved. Okay.
Does that make sense?
Yeah, it does.
If you're entering this into your calculator, you can enter this string exactly as written and you'll get this same result. I always like to show everyone how to add and subtract powers of 10 because it's a nice way to save time when you're working through problems. Does that make sense?
Yes, thank you.
Perfect, perfect. So now that we've seen another representative example, let's do another 2 practice problems. Let's work on this first cubic unit conversion. Let's spend about 3 to 4 minutes working through this first cubic unit conversion. Now that we've seen another representative example, let's try to apply what we've learned and refine our problem solving process. So let's spend about another 3 to 4 minutes on this example. And don't be shy to submit your questions and your proposed responses in the chat, and we'll discuss in about another 3 minutes. And just make sure that when you're performing these unit conversions, that you make sure to cancel out each component of the cubic unit. And we'll discuss this example in about another 2 minutes. It's great to see all these responses in the chat, and we'll discuss in about 1 more minute. Okay, so let's discuss this example. So in this case, we're starting with the units of millimeter cubed, and we're asked to reach final units of nanometers cubed. So what intermediate stepping stones will we be going through? Meter, yep. And instead of just meters, it would be meters cubed. We know 1 nanometer is equivalent to 10 to the negative 9th meter. And we know 1 millimeter is equivalent to 10 to the negative 3rd meter. Okay, so starting off, if we have 4.5 times 10 to the negative 9th millimeter cubed, and we want to go from millimeter cubed to meter cubed, what units do we need to have on top? What units do we need to have on top? Meter is exactly right. So we have 10 to the negative ninth meters per, oh, whoops, sorry. Getting ahead of myself. We have 10 to the negative third meter per millimeter. However, because it's cubed, we need to cube our conversion factor. For our next step, we're going from meter cubed to nanometer cubed. So we need nanometers on top. So we have 1 nanometer per 10 to the negative ninth meter. And again, we cube our conversion factor. So if you punch this into your calculator, you'll in turn get 4.5 times 10 to the negative ninth times 10 to the negative ninth times 1 over 10 to the negative 27th nanometer cubed, which in turn gives us 4.5 times 10 to the ninth nanometer cubed. Does this make sense to everyone so far? Any questions on this example? Is the second try a little bit easier than our first few looks at these types of conversions? Is it making more sense as we do more of these examples? Perfect. So if we don't have any other questions, let's look at this last example for unit conversions. In the most difficult example that I'm going to give you on an exam or quiz, where we have a composite conversion involving a cubic unit. So let's spend about 4 minutes on this example, and then we'll discuss. We already see some fast responses, but don't worry, you're welcome to take the full 4 to 5 minutes. And if you have any questions working through these examples, don't be shy to message me in the chat or unmute and ask your questions verbally. And the responses I'm seeing in the chat look reasonable so far. And we'll discuss in about another 2 minutes. And the responses I see in the chat look great. It's really good to see improvement throughout this chapter. And don't worry if these concepts take a little bit of time. That's why I have additional practice problems in the workbook. And let's now discuss this example. Let's make our solution map now. We have centigrams per millimeter cubed. Our end goal is milligrams per centimeter cubed. Okay? So, first things first, let's deal with the top units. We're trying to go from centigrams to milligrams. So what is our stepping stone? What is our stepping stone? Grams. So we're going to go to grams per millimeter cubed and then milligrams per millimeter cubed. Okay, for our next conversion, we want to, we want to go from millimeter to centimeter cubed. So what is our intermediate stepping stone? Meter cubed. So we're going to go to milligram per meter cubed and then to milligram per centimeter cubed. Perfect. So now that we have everything set up, so if we have 170 centigram per millimeter cubed, if we want to go from centigram to gram, we put grams on top, and we know we have 10 to the negative second gram per centigram. If we want to go from grams to milligrams, we put milligrams on top, and in 1 milligram, we have 10 to the negative third gram. So we completed our first conversion. Now, if we want to go from 1 over millimeter cubed to 1 over meter cubed, what unit needs to be on the bottom? What unit needs to be on the bottom? Meters cubed, exactly right. And we know in 1 millimeter, we have 10 to the negative third meter. But because we have a cubic unit, we cube our conversion factor. Next, when we're going from meter cubed to centimeter cubed, we're going to have centimeter cubed on the bottom, and we know there are 10 to the negative second meter per every 1 centimeter. Again, since we have cubic units, we cube our conversion factor. So that in turn gives us 170 times 10 to the negative second times 10 to the third times 10 to the ninth times 10 to the negative sixth milligrams per centimeter cubed, which in turn gives us, after punching into our calculator, 1.70. So we have 1.70 times 10 to the sixth milligrams per centimeter cubed. Does this make sense to everyone? Does this second attempt make things much more clear? Is everyone feeling a little more comfortable with these concepts?
Can you go up a little bit on your board? I'm just trying to screenshot so I can just look at it later. Thank you.
Yes, I'll be posting these annotated notes as well to the Canvas shell. Any other questions I can address? If not, let's keep going and let's talk a little bit about significant figures. So we've done a lot of unit conversion examples. That'll be really important for dry lab 2, which I'll show you in the lab manual momentarily. For the lab that we're going to focus on today, which is focused on measurements, I'm going to give you a pre-lab, pre-text lecture to help you understand and practice on taking measurements. So for significant figures are really critical to understand how to take measurements. So when you make a measurement, there are 2 types of digits recorded. Certain digits, which are digits that are explicitly recorded on the instrument or digits explicitly marked by a graduated mark. The other type of digit that we record in a measurement is known as the uncertain or the estimated digit. These are digits not marked by a graduated mark, and the estimated digit is the last digit in a measurement. The total number of digits reported is the number of significant figures. So 50.1 has 2 certain digits and 1 estimated digit. So in total, we have 3 significant figures. Significant figures, in other words, are the number of digits reported in a measurement. We often call measurements with more significant figures more precise measurements. Let's do an example, and let's look and let's try to indicate how many significant figures do the following measurements have and which measurement is the most precise. So 15.00, I see 1, 2, 3, 4 digits, so that has 4 significant figures. What about 2.0? How many significant figures does 2.0 have? 2. And what about 15.000? How many significant figures does 15.000 have? 5, has 5 sig figs. Perfect. So which measurement is the most precise? Which measurement has the most sig figs? The last one, exactly. 15.000 is the most precise measurement because it has the most total number of sig figs. Wonderful. Does this make sense to everyone? And now, this is the part that you really need to pay attention to for the lab. This is essentially what you're going to be doing the entirety of today's lab. We're next going to talk about graduated devices. Now, graduated devices are devices with markings that indicate an increment of a unit of measurement. For example, graduated centimeter rulers have 1 centimeter increments. So each of these little marks represents 1 centimeter. So this would be 61 centimeter. This next one would be 62 centimeters, etc. Each of these little marks is equivalent to 1 centimeter of distance. For graduated devices, the certain digits are explicitly noted by your graduated increments. So looking here, we have this certain digit. We have this clearly marked graduated increment that corresponds to 64 centimeters. So looking at the length of this wood block, is it greater than or less than 64 centimeters? Is the length of this wood block past the 64 centimeter line? Or it's greater, right? So our wood block is somewhere between 64 and 65 centimeters, but it's greater than 64 and less than 65. So we're going to write down 64. These are our certain digits. Now, in addition to our certain digits, we can also estimate 1 additional digit between our tick marks. So if each of these marks represent 1 centimeter, we can estimate for 1 additional decimal place, 1 additional digit. So would someone like to propose, what we estimate this wood block to be? If it's between 64 and 65, I noticed in the chat someone said 64.2 centimeters. That's perfectly fine. You can estimate 1 digit, 1 decimal place past your certain digits. So 64, that's certain. We see a clear graduated mark. And then we estimate 1 more digit, 1 more decimal place, and that's our estimated digit. So the estimated digit is the last digit that's estimated between our graduated marks in our device. So overall, this number has 3 sig fig. And the number of significant figures, as we notice, is directly related to the instrument used to take that measurement. Okay, typically you can report estimated digits up to 1/10 of the smallest graduated mark or tick. So for example, in the above example, we know that 1 tick, 1 graduated mark corresponded to 1 centimeter. For our estimated digit, you can report up to 1/10 of a tick, which is equivalent to 1/10 centimeters, which is equivalent to 0.1 centimeters. So we can report up to the 10th place. As we notice, we reported our estimated digit up to the 10th place. Does this make sense to everyone? Any questions so far? Let's keep going then, and let's take a few measurements. So I'll do this first example once again. So to figure out the value of a tick, you may be wondering, how did I know that this ruler counts in centimeter increments? So to go from 60 to 70, so to go from 60 to 70 centimeters, it takes us 10 ticks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ticks. So we know we have 10 centimeters are equal to 10 ticks, 10 of these little marks. So then 1 tick is equal to 10/10, which is equivalent to 1 centimeter. Oops, sorry. Now, to figure out the value of 1/10 of a tick, to figure out where we can report our estimated digit, we know 1/10 of a tick is equal to 1 tick, which is 1 centimeter over 10, which gives us 0.1 centimeters. Now that we have these parameters outlined, we report our certain digits. So we're around 64 centimeters. We're past the 64 centimeter mark. So we report 64 as our certain digits, and then we estimate one other digit, one other decimal place in the 10th place. So this would be 64.2 centimeters. Does that make sense to everyone? Does this make sense to everyone so far? So what I'd like you to do now is I'd like you to try looking at the following ruler, and we're going to do this example together. So this time, to go from 60 to 70, it only takes us 1 tick. So we know 1 tick is equal to 10 centimeters. So then 1/10 of a tick is equal to 10/10, which is 1 centimeter. It could also be 64.1 in the previous example. The estimated digit inherently varies a little bit. The estimated digit has some variation. Very good question. Does that make sense? Okay, so notice how when we change our ruler, now, what is our certain digit? What is explicitly marked in our instrument? 60. So we know our first digit of 6 in the tens place, our value is somewhere between 60 and 70. So 6 is a certain digit, and we can estimate in the ones place. So we'd say it's around 64 centimeters. You can just as easily report this as 63, 65, 66, because the estimated digit has variation. You typically observe variations in the estimated digit. Your certain digits are fixed, your estimated digits will vary. Does that make sense to everyone? Does that make sense? Does everyone notice how different rulers, different devices have different numbers of significant figures in their measurements? Does everyone notice how if we use a different device with different tick marks, our measurements have different numbers of sig figs? In general, the more digits you report, the more precise your measurement is. Precision, more formally, is a measure of the variability or deviation in a data set, and measurements with large numbers of significant figures are considered more precise as the estimated digit is smaller relative to your measurement. So more significant figures, more precise. So let's do an example. Suppose you're dealing with a thermometer, and this is like an old school thermometer. I'd like you to try to answer the question, how should the following temperature be recorded? So again, you need to tell me what the value of a tick mark is, what the value of 1/10 of a tick mark is, and then the overall certain and estimated digits in your measurement. So I'll give everyone about 2 to 3 minutes to work on this example, and then we'll discuss. Yep, the value of a tick mark is 2 degrees, exactly right. And we'll discuss this example in another minute. Okay, so let's discuss this example. So first and foremost, 1 tick is equal to 2 degrees Celsius. So 1/10 of a tick is equal to 0.2 degrees Celsius. So then our certain digit is in the ones place. So we can write our certain digit as 5, and then we can estimate in the tenths place. So 5.8 degrees Celsius is a perfectly valid measurement. Just as a side note, if 1/10 of a tick is even and it goes in increments of 2, your last digit should be even and be in increments of 2. So 5.7, although it's reasonable, it is a little bit more precise than the precision of our instrument. Does that make sense? So we can't report in increments of 0.1. We can only report up to a precision of increments of 0.2. So overall, this measurement has 2 sig figs. Does that make sense to everyone? Perfect. So let's now look at another thermometer, and I'd like you to answer the question, how should the following temperature be recorded? Let's spend about 1.5 to 2 minutes, and the responses I see in the chat look great so far. But let's try to get a few more responses in the chat. This is exactly the kind of measurements you'll be taking in today's lab. 28 degrees Celsius. I see a lot of measurements reported in the chat. Spend about another 30 seconds to a minute to try to get a few more responses, and then we'll discuss. I'm glad that everyone's still participating and submitting their proposed responses. And it looks like we have almost 10 responses in the chat, so let's discuss. So first and foremost, we need to figure out the value of a tick. So from 20 to 30, a tick is equal to 10 degrees Celsius. So then a tenth of a tick is equal to 10 over 10, or 1 degree Celsius. We can report our certain digit. We know we're somewhere between 20 and 30 with our certain digit being 2. And then we can write one estimated digit. So this could be 28 degrees Celsius or 27. Both are fine. Yep, exactly right. This measurement also has 2 sig figs. Does that make sense?
I have a question.
Yes.
When you said in the previous example, like because the increment was even, the estimate has to be even, would that refer to the tick or the tenth of the tick?
The tenth of a tick.
Okay, got it. Thank you.
Because that indicates the maximum precision, the maximum certainty that we can report our measurement up to. Perfect. The responses I saw for these 2 examples looked great. So let's now do some length recordings, and let's work on these 2 examples, and let's ask, how should the following length be recorded? Now, it's really important to note, you need to figure out the value of a tick and then the value of a tenth of a tick before you try taking your measurement. Note, a common trick for a lot of these problems is to give students a ruler or a graduated device that has tick marks that aren't just increments of 1 or 0.1. And that's my hint to all of you as you work through these next problems. So let's spend about 4 minutes taking these measurements, and then we'll discuss.
Professor, would you please repeat the hint? I didn't get it.
I would check to make sure and figure out the value of a tick mark, because the value of the tick mark may not be 0.1 or 1. It may be another increment.
Okay, got it. Thank you.
Let's try to get a few responses in the chat, and we'll spend about another 3 to 4 minutes on these 2 examples. And the responses I'm seeing in the chat look reasonable so far. Keep in mind the number of sig figs that you're reporting in your measurement for the first example. Let's try to get a few more responses for the first example, and we'll discuss just the first one in about another minute and a half. Okay, so let's look at this first example. So to go from 1 to 2, to traverse 1 centimeter, it takes us a total of 5 ticks. Ergo, 1 tick is equal to 1 centimeter over 5, or 0.2 centimeters. 1/10 of a tick in turn is 0.2 over 10, which is 0.02 centimeters. So thinking about our certain digits, this certain digit is 1.4, and this other certain digit is 1.6. So we can report our certain digit as 1.4, and then we can estimate one more digit, keeping in mind the estimated digit has to be even. So I'd say it's around about 1.48 centimeters. Key things to look for: your measurement should have 3 sig figs. 1.50 is also a reasonable answer because it's within the estimated digits uncertainty. Does that make sense?
Professor, why did you say it needs to have 3 sig fig? How do we know that?
Because we have 2 certain digits and 1 estimated digit.
Okay, got it. Thank you.
Perfect, perfect. Let's spend about another minute and a half to 2 minutes, and let's work on example number 2. Can I explain the tick marks again? Yeah. So going from 1 to 2, that's 1 centimeter of distance. It takes us 1, 2, 3, 4, 5 ticks, right? So 1 centimeter is equivalent to 5 ticks. In other words, 1 tick is equivalent to 1/5 of a centimeter. That's where we get this 0.2. Does that make sense? Perfect. So let's work on this next example, and then we'll discuss in about another minute to a minute and a half. and we'll discuss in another minute. Okay, so first to go from 1 to 2, so 1 to 2, which is equivalent to a distance of 1 inch, it takes us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ticks. Ergo, 1 tick is equal to 0.1 inches. Okay, so with that established, if we know 1 tick is equal to 0.1 inches, we know a tenth of a tick is equal to 0.01 inches. So now we write down our certain digits. So we have 1.2 as our certain digit, and then we can estimate into the hundredths place. So 1.23 inches would be perfectly reasonable. Again, you always want to calculate from scratch the value of a tick. Does that make sense to everyone? Is everyone comfortable with this idea?
So I got 1.24. Would that be correct as well, or
Yes,
no?
that's more than okay. Yes, there's always going to be variations in your estimated digit. Does that make sense?
Yes, thank you.
Perfect.
Get the from 0.1 to 0.01 again.
So if we take 0.1 and divide it by 10, that gives us 0.01.
Gotcha. Thank you.
Perfect. Okay, so let's do a little bit more practice on this, since we'll often be taking some length measurements as part of the lab. So let's spend about 2 minutes and let's ask, how will the following length be recorded for the following paper clip? And we'll discuss this example in about 1.5 to 2 minutes. Let's try to get a few more responses in the chat, and then we'll discuss in about another minute. Okay, so let's discuss this example. So to go from 2 to 3, so to go from 2 to 3, which is 1 centimeter, it requires a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ticks. In turn, we know 1 tick is equal to 1 over 10, which is 0.1 centimeter. And then 1/10 of a tick is equal to 0.01 centimeter. We then report our certain digits, so it's past the mark of 2.7, and then we estimate 1 additional digit. I'll go with 2.71 centimeters. There we go. And all of the responses I see in the chat look perfect. Any other questions on this example? Okay, so let's bring up one last point. Any instrument where you take a measurement from, there's an inherent uncertainty in their measurements. The last digit reported from other devices, such as your laboratory automated balance and digital balance, the last digit is always the estimated digit. Any questions on that? Okay. We're next gonna look at volumetric glassware. As we're getting close to the end of the period, what we're going to do is I'm going to give you an overview of the laboratory. We're going to have an opportunity for everyone to work on this laboratory. Next lab session, we'll cover a little bit more in lecture next Monday, and you'll be able to turn in this lab as well as dry lab 2 next week together. So I've been giving everyone a lot of the contextual information that you need to complete the lab. We're now going to switch gears a little bit, and we're going to talk through what you're going to be doing in the laboratory that we'll have opportunities to work on next class session. So allow me one moment to pull up our laboratory orientation. And I just want to talk everyone through it, so that way, if you want to, on your own time and next Wednesday during our next lab, you can start working on this lab and some of the dry lab components, or you can wait until next Wednesday. I just wanted to give everyone a pre-lecture summary of how to take measurements, because what you're going to be doing in experiment 1 are taking measurements for different graduated devices. So this is based on our laboratory manual experiment 1, chemistry and measurements. And in the lab manual has a nice, wonderful introduction section. And in the lab manual, you're going to be asked to take a series of measurements. So for each of the parts, so like measuring length and measuring volume, in the lab guide, I have provided you an introduction with the exact same name. I would read the introduction for each section. And then I have a procedure section. So for part A, I have given you an alternative procedure. And what you're going to do is you're going to take a series of measurements and enter your measurements into this table. This table is what you're going to attach and submit as part of your report. So just to show you what these pictures look like, if you click on one of the links, you'll see a picture of a ruler. This is a centimeter ruler. And you'll be able to record the length of the object in the ruler. Does that make sense? So just like what we did during lecture, you're going to be measuring the length of different objects from the photos I've provided. So you're going to
So
take the measurement.
Professor, we write it down then in our manual book, and then we take a picture of it, and then we send it to you. How do we send the picture?
Ah, yes, there's a guide in our online how-to guides to Canvas in our main course shell. Let me show you that. So for guides on how to upload photos, there's a guide under online how-to guides.
Okay.
And it's a video guide. This lab will be due not this coming Sunday, but next Sunday, because I'm still going to give you some more time to work on this lab. One thing that I'd like you to do is once you've taken your measurements, you're going to have to collaborate in the discussion forum with 2 other students, and I'd like you to compare your measurements and see whether your measurements are similar or different. Then you're going to answer discussion question 1. If you look in your lab manual, there are some pre-lab questions and also discussion questions. So instead of this part A, I've given you an alternative procedure here, and this is the table that you'd fill out. You're also going to answer these 2 questions. So how does the value of your line length compare to other students? And then you're going to answer question 1, which is what digits in the measurement are the same and which are different compared to the other students. So you're always going to answer these discussion questions. For part B, measuring volume, I provided you 3 graduated cylinders, and this is exactly the same as your lab manual. So you can directly fill in your measurements into the lab manual. And just like before, the cylinders have some pictures. Okay, so you take your measurements, and for the solid displacement, I've also provided you some pictures. And you'll record your measurements in your lab manual or using the table I've provided. Make sure you show your calculations. For the mass, rather than this lab procedure, I provided you a series of mass measurements, and you're going to take measurements from these two links. So I have the mass of an empty beaker and the mass of a beaker plus water, and you're going to take these mass measurements following sig fig rules. And then you're going to answer questions 2 and 3 in your lab manual. So that's all I'm requiring from you for this lab, and you're going to submit all of your lab manual pages with the completed questions, as well as the supplemental procedures that I've required for you to do in place of some of the lab manual procedures. And you're going to submit all of those together as a series of photos or PDFs, ideally in a PDF format that's clearly legible. You can start working on this weekend. This lab will be due next Sunday, not this Sunday, but next Sunday. And I'll also be providing you a link to lab 2. If you already have your lab manual, just as a preview for next week, lab number 2 is known as conversion factors and problem solving. Yeah, I'll be adjusting the due date. I'm providing everyone a little bit more time. I had the due dates tentatively set, but due to the issues associated with the wait list, I want to give people more time so the waitlisted students can be added and participate in the course so I can log them as having completed assignments. So I'll be adjusting those due dates. Do not worry about that. As a preview, yes.
You provide the actual lab on Canvas?
It's not the full lab. I do tell you in these experiments that you need to read the procedure in your lab manual. And the procedure name is exactly the same as the lab manual. If there's a modification, I provide the modified procedure in Canvas and the data table that I want you to fill out for that modified procedure. Does that make sense?
Yeah, so the pre-lab, that's what we do before.
Yes.
So like on a Tuesday night for us.
Yeah, and you'll turn in all the lab pages, including the pre-lab and post-lab with the questions answered and the data tables filled out.
And that should be in our lab manual, you said, correct?
Yes. Mm-hmm.
Thank you.
Yeah. And then while everyone's here, if you have your lab manual with you, the lab number 2 that I'll be assigning next week is known as conversion factors and problem solving. If you look at, it's experiment 2 in the lab manual. Does everyone see that in their lab manual? Can I just get some feedback? If you flip to experiment 2, do you see this experiment name? For those with the custom edition and the 3rd edition, do you both see this for experiment 2? I just want to make sure, just in case I need to do a page-to-page comparison. And I would always search based on the experiment name. So it's called conversion factors and problem solving. Does everyone see that lab?
For 3, the not custom one, I see it.
For what? For which
For
one?
the edition
3rd
3.
edition?
Yeah, I see
Okay,
it.
perfect. For students with a custom edition, do you also see this lab? The number may be different, but the name is the same. It's called conversion factors and problem solving. We'll be working on this lab next week. If you want to get a head start, you're more than the material that I provided you in this pre-lab lecture today will be very useful for working through lab 2. With that said, we'll continue our lecture on Monday. You're welcome to start working through these labs this weekend. They won't be formally due until next Sunday. And if you have any questions, I'll be providing more insights into taking measurements in our lecture on Monday. And both of these recordings will be posted to Canvas. So let me stop the recording for today.